And of course, you are with your left-hand side outside the curve, so you are in the external region and you are going in this direction. So you get that this direction is negative and indeed is clockwise, not counterclockwise. Okay? So I hope I gave the message without any formula. And so when it is possible not to use formulas, it is much better for everybody. And so we know what is a closed curve positively oriented. Okay? Moreover, remember that we ask for some regularity of the internal part. The internal part must be bounded. Of course, if the curve is closed, this is always guaranteed. And the curve must be regular. Okay? So, and now I can give you Green's theorem, and then the proof and some explanation of the Green theorem will go to a further video, I guess. So, here we have Green's theorem, or Gauss-Green theorem. That states the following. Okay? You can start either by the domain or by the curve, but let us start with the domain. So let D be a region of the plane with the regular properties listed before, and C be its boundary. That will be a closed curve. Not only a closed, but also a regular closed curve. Regular basically means that at every point there is a tangent vector. There are no corners, even though some corners sometimes will be allowed and we will use it. Okay? Okay, moreover, we have a field. So let F equal to F1, F2. I will put the indices by hand later. Let F, okay, we'll put now the indices. F1, F2. Be a vector field whose components F1 and F2 are differentiable, and here I want to stress this, in every point of D and whose derivative are always continuous. In mathematical notations, this means that F as a field is C1 of D. Okay? And now let us go with the theorem. Then the following identity holds. You have that, so I write it in purple because it is very important. We have that the circulation of F on the curve C is equal to the double integral, the planar integral on the region D of what? Of the derivative with respect to the variable x of the y component of the field minus the derivative with respect to the variable y of the x component of the field, dx dy. This is what is called in literature Green's identity or Gauss-Green's identity. Okay? Before closing this video, I want to give you sort of intuition, and the idea is the following. You have this gamma, and then you want to compute the circulation of the field. So for instance, here you have F, for instance, like that, but this is not a nice vector. I want to change the vector. A more beautiful vector is this one, and here you have the tangent. So you have the circulation here is equal to, so from here we compute the circulation on C of F times dr, and what you find then is that this is the circulation is equal to the double integral of this strange integrand function dx f2 minus dy f1 dx dy. These two guys are the same, even though apparently they are very far away from one another. I want to stress a point. I want to stress another point, which is this one. The curve must be also positively oriented. Of course, I introduced positive orientation in order to do that, but I have to repeat it. You are right. So, positively oriented. Otherwise, there is a sign arising. So, and another thing that I want to stress is the following, an important remark that says the boundary can be more complicated. For instance, in the case of holes, you already know that holes are quite important in this part of the theory, and so here you have a hole here. This is the region D, and then what you end up with, positive orientation, is counterclockwise in the external boundary, but here it must be clockwise, because when you go with your bicycle on this curve, are you here with your bicycle, in order to find at your left the internal part, then you have to move clockwise around this internal boundary. Okay? So be careful whenever you want to consider associate counterclockwise and positivity. This is true for the external boundary, but if you have holes, you also have some internal boundary, and everything changes. So this is the result. I did not give you any motivation for the result. In the next lecture, I will give you example, and afterwards, I will give you also a sort of intuitive proof, not a true proof, not a proof for mathematicians, but I think that for engineers, it can be good. It is also much clearer than the proof for mathematicians, and also for physicists, it can be good. Okay, see you.